Dear students, in last class we solved a problem based on designing of a linear phase FIR high pass filter using Hamming window. Today we will take a problem based on designing a linear phase FIR bandpass filter to pass frequencies in the range of 0.4 pi to 0.65 pi radians per samples by taking 7 samples of Hamming window sequence. Solution. Given desired frequency response h of e raised to j omega h of e raised to j omega is equal to e raised to minus j alpha omega for omega greater than or equal to minus 0.65 pi. For omega greater than or equal to minus 0.65 pi and less than or equal to minus 0.4 pi. And for omega value greater than or equal to 0.4 pi and less than or equal to 0.65 pi. The frequency response graph may be drawn as here now. So minus 0.65 pi to minus 0.4 pi and 0.4 pi to 0.65 pi radians per sample are the bandwidths of the given bandpass filter. Now we have to obtain desired impulse response of this bandpass filter by taking inverse Fourier transform of h of e raised to j omega. Obtaining desired impulse response hd of n by taking inverse Fourier transform of hd of e raised to j omega. So hd of n we can write as 1 by 2 pi into integration of hd of e raised to j omega into e raised to j omega n d omega between the limits minus omega c2 to minus omega c1 plus integration of hd of e raised to j omega into e raised to j omega n d omega between the limits plus omega c1 to plus omega c2. In this filter, minus omega c2 is equal to minus 0.65 pi minus omega c1 is equal to minus 0.4 pi plus omega c1 is 0.4 pi and omega c2 is equal to 0.65 pi. One by 2 pi now in place of hd of e raised to j omega we will substitute e raised to minus j alpha omega into e raised to j omega n d omega minus omega c2 to minus omega c1 plus e raised to minus j alpha omega into e raised to j omega n d omega omega c1 to omega c2. One by 2 pi minus omega c2 to minus omega c1 are the limits of integration of e raised to j omega into the bracket n minus alpha d omega plus omega c1 to omega c2 e raised to j omega into the bracket n minus alpha into d omega. Integrating we get 1 by 2 pi e raised to j omega into the bracket n minus alpha by j into n minus alpha. limits of integration were minus omega c2 to minus omega c1. So I have to put same limits here and then simplify. Next part is e raised to j omega into bracket n minus alpha divided by j into the bracket n minus alpha with limits of omega c1 to omega c2. Now we have to substitute for the limits and simplify. 1 by 2 pi into the bracket e raised to minus j omega c1 into the bracket n minus alpha minus e raised to minus j omega c2 into n minus alpha whole divided by j into the bracket n minus alpha plus e raised to j omega c2 into n minus alpha minus e raised to j omega c1 into n minus alpha whole divided by j into n minus alpha. Now we will rearrange the terms and then write these terms inside the bracket as sine of omega c1 and n minus alpha product. So we will have 1 upon n minus alpha into pi into e raised to j omega c2 into n minus alpha minus e raised to minus j omega c2 into n minus alpha upon 2j, because I am taking this 2 inside the bracket and n minus alpha outside. Minus e raised to j omega c1 into n minus alpha minus e raised to minus j omega c1 into n minus alpha upon 2j. So I will put this in bracket. Now 1 upon n minus alpha into pi into the bracket sine of omega c2 into n minus alpha minus sine of omega c1 into n minus alpha.
This is simplified expression for HD of n.
And this HD of n holds good for all values of n except n equal to alpha. To find the value of HD of alpha or HD of n at n equal to alpha, we have to go to the initial step. At n equal to alpha, HD of n is equal to 1 by 2 pi. Now see here, in this expression for HD of n, if I make n equal to alpha, then the power of e will become 0 and e raised to 0 will be equal to 1. So we will have here d omega. Similarly here also. Minus omega c2 to minus omega c1 e raised to 0 d omega plus omega c1 to omega c2 e raised to 0 d omega. Here also I will show 1 by 2 pi. Simplifying, one by 2 pi into the bracket minus omega c1 plus omega c2 plus omega c2 minus omega c1. That is equal to 1 by 2 pi to omega c2 minus 2 omega c1. If we take 2 common outside, 2 and these 2's will cancel. So omega c2 minus omega c1 by pi we will get. We know omega c2 is equal to 0.65 pi and omega c1 is 0.4 pi divided by pi. If we take pi common outside, pi in numerator and denominator will cancel. 0.65 minus 0.4 is 0.25. So this is what? HD of n at n equal to alpha. Next we will compute the Hanning window sequence for n equal to 7. Given n equal to 7, alpha equal to n minus 1 by 2, that is equal to 3, and n minus 1 is equal to 6. So write computation of Hanning window sequence. WC of n. We know WC of n is given by (0.5 pi 0.5 plus 0.5 into cos of 2 pi n upon n minus 1 for n equal to minus of n minus 1 by 2 to plus n minus 1 by 2. Equal to 0 otherwise. I will show here calculation of one value of WC of n, say for n equal to minus 3. (0.5 plus 0.5 cos of 2 into pi into minus 3 divided by 6, that is 0.5 plus 0.5 cos of here 6 and this 2 and minus 3 will cancel, giving minus 1. That means we will have here in degrees minus 180. Cos of minus 180 is minus 1. So 0.5 minus 0.5, that is equal to 0. So this way you have to compute the remaining values. I will write here the remaining values directly. WC of minus 2, WC of minus 1, WC of 0, WC of plus 1, WC of plus 2 and WC of plus 3. WC of minus 2 is equal to 0.25, WC of minus 1 is 0.75, WC of 0 is 1. So due to symmetry we can now write the remaining values directly as 0.75, 0.25 and 0. Next we will compute the desired impulse response sequence HD of n. Computation of desired impulse response HD of n for n equal to 0 to capital N minus 1. Here also I will give you one detailed computation. Next values you will have to compute. For n equal to 0, HD of 0 is equal to sine of omega C2. Omega C2 is 0.65 into pi into 0 minus 3, because alpha value is 3, minus sine of 0.4 into, this is omega c1 value, pi into zero minus 3 whole divided by pi into 0 minus 3. Here these angles should be converted into degrees, and in the denominator pi should be kept in radians only. Simplifying, you will get 0.156 minus 0.5877 by pi into minus 3, which will be equal to 0.0458. For n equal to 1 to 6, you have to calculate the values. Here I will write them directly. HD of 1 is equal to minus 0.223, HD of 2 is equal to minus 0.191, HD of 3 is 0.25, HD of 4 is minus 0.0191, HD of 5 is minus 0.223, HD of 6 is equal to 0.0458. And now we will rewrite these sequences as an array. WC of n is equal to 0, 0.25, 0.75, 1. Here 0th sample is 1, 0.75, 0.25 and 0. HD of n 0.0458 is 0th sample. Then we have minus 0.2223 minus 0.0191, 0.25 minus 0.191 minus 0.2223, 0.0458. Now we will multiply this WC of n by z raised to minus 3. That means we will delay these samples by 3 units, and then we will multiply WC of n, then we will multiply delayed WC of n and HD of n. So when I multiply this, WC of n becomes 0, 0.25, 0.75, 1, 0.75, 0.25, 0. But now 0th sample will be 0 only. Obtaining impulse response H of n. H of n is now equal to WC of n, which is delayed here, z raised to minus 3. So you can show here into z raised to minus 3 into HD of n. If we multiply sample by sample here, then we get 0 minus 0.0556 minus 0.0143, 0.25, minus 0.0143, minus 0.056 and 0. And 0. Next we'll take taking Z transform of H of n, we get H of Z, that is Z transform of H of n is capital H of Z as minus 0.0556 into Z raised to minus 1 plus Z raised to minus 5 minus 0.0143 into Z raised to minus 2 plus Z raised to minus 4 plus 0.25 into Z raised to minus 3. Now this H of Z is digital transfer function of required FIR filter. Dear students, I will stop the class here and continue in next class. Thank you.